Section 3.9, related rates. So here's another section with a little bit of application, a few application problems here. A relatively short section. I just have a few examples that I'm going to run through with you, but they are application problems involving our derivative. All right, so as is always the case with applications, I know these are always our favorite things to do in math, but when you think about it, this is the more useful stuff. I mean, what good is all these calculations? Whoop-de-doo, I can find a derivative of a function. Yay. What do I use that for? What does that tell me? So applications are actually the more useful part of this stuff. It actually gives meaning to all these different concepts that we're talking about. So what I'm going to look at in this section, related rates it's called. I'll explain why that is the title. Right. But what this is going to bring into play is the implicit differentiation that we talked about back in section 3.5. All right, so here we're going to really make sure that we understand what implicit differentiation is all about. Okay, but always my recommendations with application problems, first and foremost, you have to understand the information presented. As I keep harping on, it's all about the language. You've got to be organized. You've got to label things properly, including proper units. Units go a long way in dealing with these application problems, not just the ones in this section, but the ones that we're going to look at also in the next section as well. There's going to be some more applications, but of a little bit of a different type. So it's all about the units, it's all about the information. So let's see what we've got. I'm taking this first from the homework section, number 4 on page 249. I'm looking at, given that the length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? Right? So first, just labeling the information. Right? So I'm dealing with a rectangle, obviously. A rectangle has measurements. We usually call that length and width. So I think I'll typically call that width and that length. That's purely arbitrary as far as which way you care to label those. That's an ugly L. Let me try that again. All right, so width and length. So what is it that we know? What information are we given? We're first given that the rectangle, its length, is increasing at a rate of 8 centimeters per second. So in other words, the length is changing over time. All right, so this is when we talk about rates of change, when we talk about the derivative. We keep harping on the language and the terminology. What is changing with respect to change in what? So in this case, the length is changing. I'm getting a change in the length of the rectangle over time, so as time changes. So what I'm doing then is I'm labeling this, the change in the length over time, as dl dt. The length changes as time changes. Also, look at the units. What are the units? The units are centimeters per second. So that is the length changing in centimeters per unit of time in seconds. If you watch the units are so important. I think we just tend to overlook the importance of units and how the units can lead you in the correct direction, not only in the labeling of the information, but in the calculations that have to be done. But I can't emphasize that enough. So that's the first observation is, what are we actually talking about? What's the value? What is it measuring? In this case, it's change in length per unit time, so I'm calling it dl dt. 8 centimeters per second. And so similarly, we're also told that the width of the rectangle is increasing at a rate of 3 centimeters per second. So that's the change in the width over time. So we'll call that dw dt. What is changing? The width with respect to what? Change in time. And that's 3 centimeters per second. And also just to mention this, because the fact that they are increasing, both of those measurements, I'll give them positive values. If they were decreasing, I'd give it a negative value. So if it said that the length was decreasing at a rate of 8 centimeters per second, then I would give that a value of negative 8 centimeters per second. So we want to also include signs to represent our quantity, so increasing versus decreasing. All right, so that's the information given, right? So change in length over time, change in width over time, dl dt, dw dt. What is it that we want to know? We're asked to find, well, what's the change in the area over time at a specific point when the length is 20 and the width is 10. So since I'm looking at or finding the change in area over time, so similarly, I'm going to call that dA dt. Right? Change in area over time. And then at a specific point when the length is 20 centimeters and the width is 10. So our rectangle is just getting larger and larger and larger. There's a rate of change in the length and the width, 8 and 3 centimeters per second, respectively. And then we're asked, at a specific point in time, when the length is 20 and the width is 10, what is the rate of change in the area at that point? Well, since we're looking for the rate of change in the area, how about we start with the area function, or the area formula for a rectangle, right? So since I want to know the change in the area, or the rate of change in the area, start with the area. So I have a formula that I can use to calculate the area of a rectangle. Area is length times width, but we're interested in the rate of change in the area with respect to time. So here we're going to differentiate with respect to time. So this is why I said earlier, this is going to end up being implicit differentiation, because I'm looking at area, length, and width all as functions of time. Right. So we've already said the length is changing with respect to time, the width is changing with respect to time. We want to know how the area is changing with respect to time. So we're making each of those functions of t. So let's differentiate our equation. Right now, again, this is implicit differentiation. So my usual statement, I would say d dt on the left, d dt on the right. I'm differentiating with respect to time. So of course, what is d dt of a? Well, that's just dA dt. Now the right side of that equation is a product. It's L times W. So I'm going to differentiate with respect to time, treating both L and W as functions of time, but there's a product there. So I'm going to follow product rule. Everything is still in play when it comes to finding the derivative. And since that's a product, I use product rule, which says what? It says first d second with respect to time. So L times the derivative of W with respect to time, dW dt, plus the second times the derivative of the first, L, with respect to time, dL dt. That's implicit differentiation. Now there's our derivative, there's dA dt, and then from here it's really just a matter of plugging in your information, right? So we know the value for L of 20, we know the value for W of 10 centimeters, that's our specific point in time. We already had dW dt listed above, 3 centimeters per second, dL dt was 8 centimeters per second. So I just plugged all that information in to do our calculation. Now, again, getting back to the units, and you can, take this for what it's worth. But those of you that did trig with me know how much we harp on units. This is also a trick you can use when you're working in like physics and chemistry, where you do a lot of unit conversions and that kind of thing. Units can be used to help you in one of two ways. First of all, if you know what the unit should be for the quantity that you're trying to find. In other words, here I'm looking at the area, change in the area over time. Well, when you talk about units for area, since we're looking at centimeters for length and width, then our unit for area would be square centimeters, right? And that's change in area over time, which is in seconds, so I should end up with a unit of square centimeters per second if I do the correct calculation. So I know what the unit should be. That oftentimes can help to make sure you're actually doing the correct calculation, because if your unit doesn't come out to be what it's supposed to be, then something's wrong with your calculation. All right, the other side of that is, if I don't know what the unit should be for my final calculation, then once I set up the calculation tells you what the unit ends up being. All right, so in other words, provided you have a correct calculation, the units work themselves out. So don't overlook the units. I mean, don't just presume, you start doing a bunch of calculations And I say, okay, I know the unit here has to be square centimeters per second when I finish the calculation, and I just do a bunch of calculations and I throw on a unit. Well, make sure the unit actually matches up to what it's supposed to be, because if not, then something's wrong with your calculation. But we take that for granted. So again, all I'm doing is, for our little formula that we came up with for dA dt, I plugged in L, I plugged in dW dt, I plugged in W, I plugged in dL dt, and notice again, L and W each have units of centimeters, and then our two derivatives, dW dt, dL dt, both have units of centimeters per second. And so notice, if you do the calculations, I've got 20 times 3 gives me 60. I've got centimeters times centimeters is square centimeters per second. I've got 10 times 8 or 80, and then again I've got centimeters times centimeters is square centimeters per second. Now notice the units are the same in both cases, so we can add those two quantities. 60 square centimeters per second plus 80 square centimeters per second gives us a total of 140 square centimeters per second. And that would be our change in area over time. There's dA dt. All right. So use the units. Units are going to be important with these applications. And like I said, when we get into the next section, a little bit different type of application. And if you're not careful with the units, you can mess it up. So use it to your advantage. Second example, number 6 from that homework section. Here we're given that the radius of a sphere is increasing at a rate of 4 millimeters per second. Didn't want to do that. So the radius of our sphere increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? All right. So we're given information. What do we know? We know that the radius is changing. It's increasing, so positive, at a rate of 4 millimeters per second. So there's the change in radius over time. Again, watch your units, right? 4 millimeters per second. So I'm going to call that dr dt, change in radius over unit time. That's really the only information we're given other than our question, which is to find the rate of change in the volume over time, right? So how fast is the volume increasing, right, when the diameter is 80 millimeters? So we're looking for the change in volume over time. So there's our dV dt at a specific point in time when the diameter is 80 millimeters. So again, here, if I'm looking for dV dt, I want the change in the volume, then let's start with the formula for the volume. Now, this is one you may not know off of the top of your head, but now you do. Volume of a sphere is 4/3 pi r cubed. I'll expect that you know that formula because I've just given it to you. Volume of a sphere. And again, I'm looking for dV dt, so I'm going to differentiate with respect to time. Now, one other observation, notice that this formula requires the radius, not the diameter, right? We're given the diameter in our problem of 80 millimeters, but the formula for volume requires the radius. So there's our value for the radius. So when the diameter is 80, the radius is 40, right? Half the diameter. All right, so let's differentiate. Now again, differentiating with respect to time. So that is d dt of the left and d dt of the right. Now, be careful here. I know I see a lot of issues here with this type of formula because remember, pi is just a constant, right? The only variable in this equation, the only variable on the right side of this equation is r, the radius. Pi is a constant. 4/3 is a constant. So when I differentiate 4/3 pi r cubed, that's a basic power rule. That's all that is. 4/3 pi is a constant. That's, call it your coefficient of r cubed. So it's 3 times 4/3 pi, which will knock out the 3, leaves me with 4 pi r squared. So here's the derivative of the left side, right? d dt of v is going to give us dv dt. And then the right side is power rule. It's 3 times 4/3, which is 4 pi r squared. Chain rule times the derivative of the base of your power function, which is r, with respect to t. So that's the thing that's going to trip you up more than anything else. It's this whole implicit differentiation thing. So first of all, what am I differentiating with respect to? And then secondly, when you do actually differentiate, follow your normal differentiation process. All right, but it's a little bit trickier here because we're not just dealing with x and y, right? We're dealing with formulas involving different variables. So that's why I keep saying you have to be clear in terms of what the variables are that you're working with, what they represent, what is changing with respect to what am I differentiating with respect to what. And in this case, I'm differentiating everything with respect to t. So I have to treat v as a function of t. I have to treat r as a function of t. So the 3 times 4/3 gives us 4. Pi is still there. R squared then times the derivative of the base r with respect to t, dr dt. And now again, that's the tricky part, because once you have that done, then I mean that's what I need, right? So here's dv dt, and here's a formula for dv dt. So I'm just going to plug in place of r, we said 40 millimeters. And in place of dr dt, right, that was given in the problem, rate of change in the radius was 4 millimeters per second. So I went ahead and plugged all that in, do my calculation. I've got 4 times 40 times 4 gives you, or actually 40 squared, don't overlook the square here. So 4 times 40 squared times 4 gives you 25,600 pi. And then we've got, notice what, millimeters squared times millimeters, which gives you millimeters cubed per second. And that should make sense because, again, what is it that we're calculating? Change in volume over time, right? We said area units are squared, volume units are cubed. That's a 3-dimensional measurement. So that works out. It's millimeters squared times millimeters cubed. So, you know, and you'll see this given 2 different ways. I mean, so this is just leaving the pi in it. So it's the 4 times the 40 squared times the 4. Or if we use the pi approximation or approximate pi, plug that in 3.14, or use the pi button on your calculator, then just rounded it to the nearest hundredth in this case. So whichever way it's asked for, if we want the exact value, we leave the pi in it. If we want to approximate it, then we can approximate the pi value and round it to whatever number of decimal places we care to. Okay? So yeah, I mean, it's not a difficult calculation. The issue here is getting it set up, right? So you've got to work with your formula for whatever the quantity is that you're measuring, and we're differentiating with respect to t, with respect to time. This third one is it's more generic, right, than the other 2, which were specific. So, but it does, you know, it brings up a little bit of calculation stuff, some funky numbers a little bit, but it's really just generic. So I'm looking at, this is number 10 out of that homework. So I've got the equation 4x squared plus 9y squared equals 36. Given that both x and y again here are functions of t, right? So we're similar to the previous in that we are differentiating with respect to t. And I'm just doing the first part of number 10. There's a second part to it, which is pretty much the same. It just changes the values. But we're asked to find, or given, that if dy dt is 1/3, we want to find dx dt at the point where x equals 2 and y equals that funky number 2/3 square root of 5. All right, but again, nothing different than the previous 2 examples. We're given the equation. So I've got 4x squared plus 9y equals 36. But again, since x and y are both functions of t, then I am looking at differentiating both sides of this equation with respect to t. So d dt of both sides. So on the left, okay, so power function 4x squared, again treating x as a function of t, using our power rules, gives me 8x times the derivative of the base with respect to t dx dt. Plus 9y squared, the derivative there, again a power function. 2 times 9 is 18 times the derivative of the base y as a function of t, so dy dt. And then the right side, which was 36, that's the derivative of a constant. We said, I don't care what you're differentiating with respect to, the rate of change of a constant is always 0. Right? So d dt of 36 is 0. And now we have an equation, you know, there's our derivative, we've done the differentiation, and then we're just going to plug in the information that's given. Right? So we're given a value for dy dt of 1/3, plug that in. We're given a value for x of 2 and y of 2/3 square roots of 5. So we're plugging that in. And so there's our x. Let's see, x, and there's our y and our dy dt. So that's the information given in the original problem. And then we're asked to find dx dt. So there's our unknown. So once I plug everything in, I'm just solving that for, excuse me, I'm just solving that for dx dt. So I trust that you can solve a basic little equation. There are some tricky little calculations in there, so make sure you can actually do those calculations and solve it. And if you solve that for dx dt, you should get negative square root of 5/4. So see if you can do those calculations. Make sure that that does come out correctly. But that's all that is once you plug everything in. Okay? So that's the types of problems. That's why we call these related rates, because you're actually looking at the rate of change of your quantity with respect to another variable, right? Or a third variable in this case. And most of the time it's time. It doesn't have to be time, though. Time is most common because we're typically dealing with rates of change over time, but that's not necessarily going to have to be the case. And when we look at the next section, we'll talk more about that. But that's it for that section.